This is a problem in which a 10 kilogram mass is attached to a rope that goes around a pulley, around another pulley and back to be attached to the ceiling. And from this pulley is hanging 3 kilogram mass. And we're told that this surface is frictionless. There is a hint that's given in this question that says that notice that this 10 kilogram mass, when it moves, let's say it moves a meter in this direction to the right. If it moves a meter here, that meter of line in the rope is going to be distributed on these two parts of the rope for this 3 kilogram mass. So in other words, when this moves a meter, this mass is going to move down by just half a meter. So that is to say that the acceleration of this mass is going to be twice the acceleration of this other mass. So knowing that, let's start thinking about the problem. First of all, I think this problem is going to be in non-equilibrium. Both masses are going to be moving with some acceleration. This is because there's tension in this rope that is not balanced by any other force. So for sure this mass is going to be moving because there is a net force in the x direction. And if I propagate this tension in the rope, it looks like it's going to be, if the mass is moving this way, then there's going to be tension in the rope towards the up. And that tension is going to be transferred to the ceiling over there. And it looks like this mass is going to be, if the 10 kilograms is moving to the right, then the 3 kilograms is moving downwards. Okay, so if I label the tension as T, then all of these are going to be T's. Okay, so first thing I'm going to do after that is I'm going to draw a free body diagram for the 10 kilogram mass and for this combination of mass and pulley for the 3 kilogram. So for the 10 kilogram, there's of course a weight for the 10 kilogram, and there's a normal force with which this surface responds in the y direction, and of course there's a tension in the x direction. So I'm going to call this my x direction, this is my y direction, and there's a tension here, and there's movement, there's acceleration in this direction. And since we said that the acceleration of this mass is going to be twice the acceleration of this other mass, I'm just going to label this as 2a, and the acceleration of this mass is going to be just 1a. So speaking of this mass, let's draw the free body diagram for the combination mass and pulley. And the reason I do that is because I noticed that there are two strands of tension here pulling this pulley up, which means that the tension in this other rope that is just connecting the pulley to the mass is going to be twice T. But I can do the same thing if I just isolate this part of the problem. I can see that, first of all, there's the weight of the 3 kilogram mass, which is going to be 3g. Sorry, I forgot to write 10g here. The fact is this really doesn't matter. The y in this case doesn't matter because there's no friction. If there was friction, I would care about this y because the friction force would be proportional to the normal force, which I would figure out knowing what the weight is. But in this case, it doesn't matter. Here, the y matters because this tells me something about the tension in the rope. And like I said, if I look at here, I find that there are two equal forces of tension pulling the pulley up in the plus y direction. And in the x direction, there is nothing. There are no forces on this mass or pulley. And so this is it. There is, however, acceleration. And since I labeled for the 10 kilogram I labeled it at 2A, then I know that this one is going to be just A. Okay, so let's solve Newton's second law for both of these. Here, like I said, the y is not really important. It's just going to say that the normal force is equal to the weight, but that's neither here nor there. But for the tension force, because it is the net force in the x direction, it's going to be equal to the mass of the 10 kilograms, which I'm going to call capital M, multiplied by the acceleration, which is going to be 2A. So this is tension equals mass times acceleration. So I'm going to call that equation number 1. If I look at the y portion of this, for this mass and the pulley, I find that in the positive y direction, by the way, I could have chosen this to be my positive y in this case, right? I don't have to make the same choice for both of them. So let's do that actually, just to show you that it's possible. And it actually makes a little bit more sense to do it this way because the acceleration is in the down direction. So I'll just make that my choice of positive y. And then I'm going to write my net force to be equal to things that are in the positive minus things that are in the negative. So in this case, it's going to be the net force in y is equal to the mass times the acceleration in y. And the net force in this case is going to be W minus 2T, and that's going to be equal to the small mass multiplied by the acceleration, which is A. And I'm going to call that equation 2. So in this question, I'm asked about the acceleration of this big mass and the tension in the rope. So to do that, using these two equations, I know this big mass, I know this small mass, I know the weight of the small mass, and I'm missing the tension and the acceleration from both equations. I have two equations I can solve for two unknowns. First of all, let's put the numbers in. So the big mass is 10 kilograms. So this equation is equation 1 is gonna become G is equal to 20A. So this is equation 1 still. And equation 2 is gonna be, the weight here is 3 times G. So that's 3 times 9.8 meter per second squared. And this was a 3 kilogram minus 2T is equal to 3A. That's equation 2. So let's see. If I want to eliminate T from these equations, what I would do is I would multiply this equation by 2 and add it to this equation. In other words, I would write 2T is equal to 40A, and I would add this equation to this equation, knowing that this will have a contribution of 2T and this would have a contribution of minus 2T. So equation 1 plus equation 2 is 2T plus 3 times 9.8 minus 2T is equal to, I'm adding equations, so I have to add the right hand sides, and that's 40A plus 3A, that's 43A. These cancel, and I'm left with 43A is equal to 3 times 9.8, so that means that A, the acceleration, is equal to 3 kilograms times 9.8 meter per second squared divided by 43. Yeah, so if I had kept the units here, this is the mass, so this is kilograms, and this is the mass, so this is in kilograms. So I know that this 43 comes from kilograms times acceleration plus kilograms. So this is a kilograms. So I expect the acceleration to be in meters per second squared. So if you work this out, you'll find that this acceleration is 0.68 meter per second squared, which means that the acceleration of the 10 kilogram mass is equal to twice that, right? Just like we said before. And that is going to be equal to 1.37 meter per second squared. And once I found that, I can plug that back in to this equation, and I can find that the tension is equal to 13.67 newtons.